Hello.
Hello. How are you doing?
Good. How are you?
Great. What are you up to?
By the way, the sunshine at your place is very nice.
Yeah, but it's because it's kind of still day. It's like 5, so.
Yeah, but I mean, even it is 5, it's still very nice because in Kunshan it was raining for a whole month, and well, it's
Oh, is it always like that?
at a particular season, yes, it is around June, July, yeah, and it's raining today. Whoa. You can never expect your clothes can be dry. So, but it's okay. Yeah, I think it's going to be okay until probably this week.
I see. Is it because it's close to ocean?
Maybe one of the reason may be that, but another reason might be it's very close to not really the ocean, but also for some river and lake. It's very close to the big lake, right? So
Oh,
I don't know. Yeah, I know very little about geography. So yeah, don't trust me. So
I don't know if lakes affect rains that much. Like, I mean, I know they can affect rains, but like to make it like a month long, that's a lot.
yeah, well, last month it was really well, kind of very terrible because it's raining all the day and everywhere just water, so I can barely. Well, I don't really want to go out because of the raining.
Oh, I see. So, I mean, it would be nice if it was raining most of the time because people would actually stay on quarantine. But it's really shiny outside, so people are like, "Oh, what quarantine? What is quarantine?"
That's true. Well, uh, well, I
Hey,
think that we have everybody here. So today,
yeah.
everybody is here on time. That's great.
Who is presenting today?
Okay. Maybe we'll start.
Yay!
Let me share my screen first. Can anybody see this?
Yes, I can.
Oh, okay. So let me briefly summarize what we have discussed before. So for this section, we just discussed how the epsilon delta definition related to our metric topology and the convergence sequence definition related to the metric topology. So we just start to discuss how to construct continuous functions in this topic. So So do you have any questions before? So because we have only 2 people last time, so if you have any questions about what we discussed in the previous contents, you can ask me now. Okay, if not, I will just continue for the next theory. So this theorem basically about, as shown in this slide, if X is a topological space, and if Fg are continuous functions, then F plus 3, F minus 3, and F multiplied by G are continuous. And if Gx is not equal to 0 for all X, then F divided by G is continuous. So based on the lemma 21.4, it is relatively easy to prove this. Anybody have good ideas? Okay, so if not, I will just briefly discuss how to prove this. So let me maybe let me recall you about the lemma 21.4. So basically, it's about the addition, subtraction, and multiplication operations are continuous functions from R cross R into R. And the quotient operation is a continuous function from R cross R minus this 0 set into R. So in this theorem, you can see that we have this addition operation, minus operation, and multiplication quotient, right? So we can relate the proof to the lemma we proved before. Basically, we just need to construct a new function here. Here. And use this addition or subtraction, multiplication, these operations. So this one is from maybe from X to R cross R. This is a continuous function as fx and gx are continuous functions. So, and from this hx to R, we can use the lemma we proved before. It is also continuous. So this whole thing can be seen as a composition of 2 continuous functions. So these 4 operations are all continuous. Any questions? No? Okay. I think it's not hard to understand, right? So I will just go next. It's about the uniform convergence. the definition of uniform convergence is that if we have a sequence of functions fn from x to y, yes, x is just a set and the y is a metric space. Let D be the metric for y. We see that sequence fn converges uniformly to the function f if given epsilon larger than 0. There exists an integer n such that D, the metric of these two functions, less than epsilon for all n larger than n and all x in x. So I will introduce an exercise in this section, like to help you understand this definition further. In the after we discuss this, all of these contents. Okay. So based on this definition, we have one theorem, 21.6 is the uniform limit theorem. It basically says it let fn x to y be a sequence of continuous functions from the topological space to the metric space y. If fn converges uniformly to x, then f is continuous. Yes, I think the theorem is maybe not hard to understand. But how to prove it? Do you have any ideas? If not, I will introduce the proof. So basically, if we want to like prove that a function is continuous in this topology topic, basically, first we want to show that if we have an open set in this Y, and we want to show that F, the inverse of Fv, is also open in X, right? So also we can like transform it in this way. If we have a point belongs to V, there is a neighborhood of we have a point U, sorry. If we have a point U, where U is an open set in X, we want to show that there always exists like a neighborhood. Sorry. Let me rephrase this. If we have a point x0 belongs to U, sorry. If we have like an open set in Y, and we want to show that the inverse of Fv is an open set in X, right? So maybe it is very hard to prove at first. So we may be transformed into this. If we have an open set in Y, and x0 is a point, random point in this set, and we want to show that for this point, we can always find an open neighborhood U, such that Fu belongs to V. okay, I said she will leave for 30 minutes or so. So maybe we just continue since she said that she has seen this before. So for this proof, we need to, for any x0, we want to find an open neighborhood of it, right? And we need to show that fu is an open set in V. That's basically our main thought. So how to prove this? I think the textbook lists three very important relations, and this connects the fx, and this connects the continuous relations between two important functions. Let me just write here. So remember that currently we have an open set in Y, right? V. And for this open set V, we can always find an epsilon ball, right? The epsilon f x0 epsilon, right? We can always find this epsilon ball. So if we want to show that this neighborhood is a subset of V, we can just show that this set, this is just belongs to this ball, right? This is just a subset of this ball, and this ball is a subset of this, right? So how to prove this? Currently we have a point fx0, right? And we want to show that the metric between fx0 and fx is less than epsilon. That means it is in this epsilon ball, right? So our main task here is just to connect these two functions to see what's the metric between them. So how to connect them? These three inequalities is very important. So first we have this relation. That is because the convergence, since Fn converges uniformly to X. So for some n, for some integer n, we can find this relation, right? By the definition of the convergence. And we can choose the metric is less than epsilon over 3. Also for this one, this by the choice of the neighborhood U. And that is by the definition by the definition of the continuity of this Fn x, since each Fn is a continuous function. So if we choose a proper neighborhood U, we can find the metric between these two is also less than epsilon over 3, right? And for this one is also by the convergence. If we choose an appropriate n, we can find the metric between these two is also less than epsilon over 3. Right? So if we use the triangle inequality, add these three terms all together is of course less than epsilon over 3. Is of course less than epsilon, right? And these three sums are larger or equal to this. So that means the metric between these two functions is less than epsilon, and we can maintain that x0 is in this epsilon wall. Any questions here?
Just a very quick comments. So you can see that
Okay.
this theorem you learn from analysis course is actually just a topological theorem. Okay, just something talking about the topology, not really analysis in some sense.
Yes. Yes, Okay, so other comments or questions? Okay, if not, I will go next. So next is a lemma, like the author mentioned in the textbook, and he leave it as an exercise for us. So I just I copy that here. The lemma basically says that like here, let x be a set and let fn x to r be a sequence of functions, and let this be the uniform metric on the space Rx. We want to show that the sequence fn converges uniformly to the function f, if and only if the sequence converges to f as elements of the metric space. So that means the notion of uniform convergence is related to the definition of the uniform metric. So do you remember what's the definition of the uniform metric? Can anybody like recall us? What's the definition of the uniform metric? Is anybody here?
just checking the definition in the text.
Oh, okay. Thank you.
Should I read it or?
Yeah, you can read it to us. Thank you.
Okay, so if we have an index set J and points X, which equal the collection of points X alpha such that alpha belongs to J, and Y, which equal the collection of points Y alpha such that alpha is in J of Rj, then we define the metric P. It's not P, I forgot the Greek name for the letter. What's the Greek name for the letter? Okay, I'll call it P. Let us define a metric P on Rj by the equation P of xy is the supremum of x alpha and y alpha for alpha belonging to J. The supremum of D of x alpha and y alpha where alpha is in J, where D is the standard bounded metric on R.
Yes.
And
Thank you.
yeah, okay.
Yeah. So, yeah, I don't know. I'm not sure when the notion of this, the pronunciation of this is, sorry. Of this one, maybe it's rho, or I'm not sure.
Yeah, it is rho, right? It is rho bar, RHO, right? RHO in the text.
Yeah, yes, right. Yeah, it's rho bar. So, so basically, we can like write it here. It's upon my understanding, it's like so we have J dimensions maybe, so R is one of the dimensions, and in this one of the dimensions we have points, right? Like in the real line we have 2 points, maybe X and Y, and we have a metric like the X, Y. So the bar xy is defined as the minimum of the xy and 1. So the largest value of this d bar is 1. And the rho bar is defined as the supreme rim of all these d bar. So its largest possible value is 1. Yeah. I think it's just the largest among the smallest values of all dimensions. So it's like the intuitive understanding. For this proof, do you have any ideas? So intuitively, I at first glance, I think this lemma holds. That's because when Fn uniformly converges like to some function, that means these two functions very close. That means these two functions, like in the maybe in the topology language, that means for any point, the two functions, one of the functions is in another functions like epsilon ball, right? So that means these two functions very close. And this statement, the sequence F1 converges to F as elements of the matrix space Rx rho bar. That also means like satisfy some metric relations, right? So maybe we can use some metric relation to connect these two statements. Okay, maybe it's hard to see at first. So I will just introduce the proof for you. I will erase all of this first. So currently we have, like, we want to show the equivalent relations between these two statements. So we have two directions. First, we want to show uniform convergence to elements of the matrix space. So how to show this? If we know that Fn converges uniformly to the function f, and this f must contain some like epsilon ball. Right? And since we know the uniform convergence, so there is some like integer n such that when n larger or equal to this n, we have that this metric between the fx, fnx is less than epsilon over 2. Right? So we have that so this equality holds because d bar is epsilon less than 1, so this holds, this equality holds. Right? So that means that in this rho bar metric, the metric between fn x and fx is less than epsilon. That means fnx is in this the rho bar ball. Right? So that means Fn converges to F as elements of the metric space of this space. Right. So basically, I think we just use some like metric transformations from D to this rho bar. Right. In this D metric, we know that it's we said that it's less than epsilon over 2, and we find that in this rho bar metric, this of course less than epsilon because this D is less than epsilon over 2. So we prove this convergence. Any questions for this direction? Okay, if not, do you have any idea for the other direction? I think it's very similar to some like metric transformation. Okay, maybe I will erase this all first. Do you have any questions? If not, I will erase all of this. Okay. So the other direction is from the conversion as elements of the metric space to convergence uniformly. So maybe I will give you a hint how to define the B rho bar of. We can set this delta as inf epsilon over 2. So this one is like the opposite of the superior. You can like for this discrete for this tool you can understand as the minimum, but for infinity many values it's just like the largest among the like for all of these elements in this set is larger than this inferior, but yeah, but it's the largest one. You can understand it as the minimum and in this context. So let's just follow this to write the proof. So if we know that this is like Fn converges to F as elements of the metric space, this one, we know that there is an integer m. So when n larger or equal to m, then Fn belongs to this ball, right? This is from the convergence. Right, so we can do remember this. The rho bar is the superior of the D, right? So that means all of this D, any of this D is less than or equal to delta, right? Okay, since we define this delta is, of course, like less than 1. That means that's because if epsilon larger than or is less than 1, we can, this one is the smallest, right? So delta equals this one. If epsilon larger or equal to 1, this is the smallest. So always we take some number less than 1, right? So d bar equals the D between Fn and F. That means D Fn F less than or equal to delta. And this delta, of course, less than epsilon, right? As we discussed here. So by the definition of the uniform convergence, we can conclude that Fn converges to F uniformly. Is that okay? I'm not sure whether you quite understand this. So if you have any questions, feel free to ask me. I will be more than happy to answer these questions. I'm not sure whether like my talk is clear or somewhere not clear. It's not clear. I'm not sure.
Sorry, do you mind going over this part again? The entire thing, probably, because I'm a little bit lost.
Go over all of this proof or just this direction?
This direction, yeah.
This direction, okay. So, okay. So this direction, we want to prove that from the convergent, from this statement, the sequence Fn converges to F as elements of the metric space Rx rho bar, right? So what's this mean? What's this statement tell us if the sequence Fn converges to F as as elements of this space? That means the metric, if we see it as an epsilon ball language, that means any Fn belongs to the epsilon ball of this F, right? And this delta, we can like set it as any value. And this row bar is the metric in this metric space, right? So Fn converges to F as elements of this metric space. That means Fn belongs to the epsilon ball of this F for any delta, right? So the main task here is to choose what delta here. So one choice is that we choose the infimum of epsilon over 2 and 1 over 2. This one can be seen as the minimum of these two numbers. So we always choose the minimum of epsilon over 2 and the 1 over 2. So why we choose these two numbers? Since there are two cases, if we of course know that epsilon larger than 0, right? But if epsilon larger or equal to 0, this one is the minimum, right? Since this one is always larger than 1 over 2. But if epsilon less than 1, this one is the minimum, right? So we choose the minimum of these two numbers. And you can notice that the minimum of these two numbers is of course less than 1 in either of these two cases, right? So that's what we get from this statement, and we just do it further. So we know that Fn is in this epsilon ball, right? And the row bar is defined as the superior of this d bar, right? Since this row bar is less than delta, this d bar is of course less than delta, right? And since this delta is less than 1, so this d, of course, less than 1 or less than delta. These two are equal because d bar is less than 1. So these two are equal here. So this one is less than delta and delta less than epsilon. So that means the metric between Fn and F is less than epsilon, and it always holds. So by the definition of uniform convergence, Fn converges uniformly to F. Is that more clear than before?
Yeah, I think it's better now. I mean, I understand it better. Thank you.
Okay. So if any other questions? Like I think it's the metric transformation we choose like proper that metric in these two spaces to satisfy some inequality to complete the proof. Okay, so
well, I just have a very quick, maybe not so relevant comment on this. So you can see that notation here is r to the x, right? So this is how you understand this r to some power, right? For instance, r to the omega. You can think is some kind of space like r multiply itself for infinite many times, countable many times, or you can also think it as all the functions maps omega, which is all the natural numbers, to r. Okay, so this is a way to understand this kind of infinite many product of the space. And then you can see that, okay, then this uniform metric is just say the maximum of this if you try to think f as a sequence, then it will be the maximum of this sequence, of the element of the sequence, right?
Mm-hmm. So can you explain a little bit more? I think I feel a little lost here.
So about what? About R to the X?
About the sequence, like
Yeah. For instance, well, if it is something like R to the power little n, right? Rn. Then what is Rn? Well, Rn is you have n component for each element in this Rn, right? But also
right.
you can also think it is nothing but all the functions from n, little n to R. What does that mean? That simply means this function has n value. Well, has you can have n input, f1, f2, f3, f4 until fn, right? And f1 is in R, f2 is in R, f3 is in R. So it can be seen as a function from a set contains the element, contains a natural number 1, 2, 3, 4 until n to this real number R. Okay, so all these kind of functions can form this R to the power n.
I see. Oh, okay.
You see that?
Thank you.
Yeah. So which is kind of a way to understand what is R to some power. You can always imagine it's just some function, okay, from this power to R, the collection of all these kind of functions.
Oh, okay. Thank you. Yeah. Okay, I will go next. Yeah, the textbook gives us two very good examples, I think, and it's a little bit more complicated. So I will try to explain it to you. And next, we'll do one exercise to help you understand the definition of the uniform convergence. So first, let's see the example 1 in the textbook. So it says that the, I will write here. This R omega in the box topology is not metrizable. So the basic idea is to use the sequence lemma. So we want to show that this R omega in the box topology does not satisfy the sequence lemma. It's the lemma 21.2. We proved last time. Do you remember it? Maybe I will read it for you. So basically it says, I will write it here. If we have a topological space X and we have a,
wait a moment. It seems Tadara is out of line, right? Where is her? Where is she? She. Let me ask. Okay, you're back. Great.
Okay. Okay, Tadora, do you have some confusions here?
I have a lot of confusions because my internet broke down literally before you changed the slide.
Okay, so I will explain it again. This writing is not related to this question. This is the exercise I want. I want you to like practice. So we are discussing the example 1 and 2 in the textbook. I think these two are good, but maybe a little hard to understand. So I write it here. So this is the first example. R omega in the box topology is not metrizable. And the basic idea to show this is to use the sequence lemma. we proved in the last time, the 21.2. So basically it says that if we have a topological space X and we have a subset A of X, so if there is a sequence points xn of A convergent to X, then xn belongs to A closure. So and the converse holds if X is matrixable. This is the sequence lemma. So we want to show that our omega in the box topology is not does not apply to this sequence lemma. So I will show it here. Why does it not hold? First, we want to show we want to find a proper A, right? We define A as following. So basically, A is all the points where each coordinate, like each number is positive. And we define a 0 point in this R omega. So it is basically all of these coordinates is 0. So we assert that 0 belongs to A. That's because by the sequence lemma, if we have a not sequence lemma, the theorem 17.4 or 5, I think, if we have a basis element in the box topology, we write it this way. Right, and if it's a basis element containing this 0, it of course intersects A. That intersects A. That means it intersects A except 0 and at other points except 0. So that's because maybe I can draw it here. So maybe in the 2-dimensional space, I think A is all the points here, right? With the coordinates positive. And B we can consider maybe this way. Right, it contains 0. And so it intersects A, right? So you can draw it B randomly, and you can always find that it intersects A. So a more rigorous proof might be if we use this point, 1/2 B1, 1/2 B2, and so on. This point is of course in like the intersection. Okay, so yeah, so we just have conclusion that 0 belongs to A closure. Sorry, here. So by the sequence lemma, we want to show that this topology, this R omega is metrizable, right? But we know that this zero belongs to a closure, but we cannot find a sequence of points xn that converges to x. So why can't we find this sequence? If we define a sequence this way, maybe a little messy here. I will erase some parts. Okay, so if we define a sequence of points this way, and these points are elements of A. That means each coordinate is positive, right? And from this point, we can construct a basis element B prime. Okay, this basis element, of course, containing zero, right? But we cannot find a sequence like in this basis element. That means this sequence of points does not converge to zero. Why this is the case? Because so if we consider a point x and n, it does not contain in any of these interval, right? Because it is open. So that means yeah. That means this sequence of points does not converge to zero. Any question here? So since if this sequence of points like converges to zero, that means it must in the basis element. But in the sequence of points x and n does not belong to any of this interval. That means it does not belong to this interval, this basis element. So this sequence does not converge to zero. So the sequence lemma does not hold for R omega in the Boss topology. So it is not metrizable here. any questions? It's one of the examples. I think this example is relatively easier than the next one. Next one is, I feel, hard to understand.
Again, to understand this kind of examples, you have to be super clear about this. First, the definitions, and also the theorems we have proved. Okay, because the second part is also important because the theorems we have proved, it might be okay at the first glance because it satisfies your intuition, you learn in analysis or calculus class, but then you have to tell the difference between the theorems you learn in analysis class and the theorems you learn in this topological class, in this topology class, because there might be something different.
Right. Yes. So if no more questions here, let's discuss the next example. So the next example is about an uncountable product of R with itself. It's not matrix. Yeah, so how to show this? First, we define countable index set is J, is the index set, and is uncountable. So also we need to show that this Rj does not satisfy the sequence lemma. In the product topology, here we discuss the product topology. So let's define A first. What's the A in the sequence lemma? A, we can define A be the subset of Rj consisting of all points X alpha, where X alpha not very rigorous, but to help you understand, for finitely many values, alpha, this is the coordinate is 1. So that means we have finite values of 1 here.
I think your notation is slightly weird to me because I think it's X alpha equals to 1, right?
Yeah.
Otherwise,
maybe.
it will be super confused.
Yeah, I will erase this. So X alpha equal to 1. So maybe we can write this way. So for any point in A, we have finite many X alpha equal to 1. right here. And then we define a 0 in this Rj space. It is still all coordinates equal to 0. But it's uncountable, but I try to write it this way, might not very rigorous. So we first, similar to before, we assert that 0 belongs to the closure of A. How to show this? So similar than before, we first find the basis element containing 0. So the basis element of the product space we can define this way, right? And U alpha does not equal to R for only finitely many values of alpha, right? So that we define the X alpha as this way. For finitely many, for alpha equals to R1, alpha 1, alpha 2 to alpha n. So that's the numbers that U alpha does not equal to R. We define this X alpha as 0 and the other X alpha as 1. Then this points X alpha belongs to A intersects U alpha. So let's say it's more like, let's say it again. So it belongs to the intersection of these two sets. That means it belongs to this A and of course the basis element. So why it belongs to A? Remember that we define A as all these points X alpha such that for finitely many values alpha, such that X alpha equals to 1, right? That means finitely many coordinates is 1. Right? Sorry here. It is, so we have defined that X alpha be the points of A defined by, so X alpha is already in X alpha. We do not need to like confirm it here. We just use the X alpha in this set and to change some properties. Sorry for that. So these points of X alpha is already in A. We just need to show whether it is in this basis element. So why it is in this basis element? The basis element contains points that for finitely many point values of alpha, U alpha does not equal to R, right? That means it like some open intervals maybe, or like some just some like infinite, just some like finite set maybe. Yes. So we define X alpha as so maybe I will write it more clearly here. So U alpha the basis element, we define it this way. For values alpha equal to alpha 1, alpha 2 to alpha n, U alpha does not equal to R. And for this sequence of point x alpha, we define this way. For alpha, also for this alpha, x alpha equal to 1, equal to 0. So, and this basis element containing 0. So this is contained in this basis element. Is that clear enough now? Yeah. Since belongs to the intersection of these two sets, that means x alpha belongs to 0 belongs to a closure. Any questions so far? Okay, great. If no questions, let me go next. So let's use the sequence lemma. We already showed that 0 belongs to a closure, but we want to show that we cannot find a sequence that convergent to 0. Then we can show that we can see that this uncountable product is not matrix, right? So basically our main task next is to find a sequence that does not converge. So we must conclude that we cannot find a convergent sequence to 0. So how to prove that? I will erase this first. Okay, maybe I will just clear all of this. So, like before, we want to find a sequence of points. We also denote it as an. So, remember that we defined an index set J before, right? This J is an uncountable index set. That means it is uncountable, of course. So we define a subset of J, is Jn. This subset consists of those indexes A alpha, for which the alpha coordinate of this A is different from A1. So that means this coordinate is different from 1. This x alpha is different from 1. So this is just one definition. So we select these points, that means. And these points like consist of Jn. So we can see that Jn is a countable set. right? Do you know why? I want to confirm that you are following me, since it is very easy to lose here. Does anybody have idea or comments here?
Is it because we defined x alpha equals 1 for over finitely many values of alpha, this the indices alpha would be the indices alpha for which okay, sorry. It's basically all the indices alpha for which x alpha is different from one which are finitely many by definition of Theorem's above.
Yes, I think you got that. You mean that alpha is finite, right?
Yeah.
Yeah, since we defined that alpha is finite, right? So, and we define this Gn, this all the unions of Gn is a countable set. That's because Gn is all the unions of these finite sets, and this union is a countable union. Right? Okay, I want to confirm that you understand here.
I think I get it.
Oh, okay, that's great. So, but we know that J is uncountable, right? Jn, the union of Jn is countable, but J is uncountable. That means there is some index in J. Let's define it as beta. Is uncountable. Not uncountable. That means this does not in the union of these sets, right? In any set of Jn. Right? So remember that we define the set Jn as the points that the alpha index, the coordinate is different from 1. Right? That means this beta coordinate equal to 1. Right? Because it does not belong to this set. So some x beta is equal to 1. So for the points x alpha, there is a coordinate beta is equal to 1. Right? So for this beta, we can consider it as a dimension. We choose we use this index and choose an open neighborhood, an open interval, maybe. U beta -1 to 1 in R. And we define U as this open set. So notice that this does not contain 1, right? So this one does not contain the 1. But 1 is contained in this set, these points XR. Or we see it as AN. Right? So this AN, this sequence of points does not belong to the basis element, right? Any questions so far? So similar to before, we find a neighborhood U that does not contain any of these AN. So AN does not converge to 0. That means this uncountable product of R is not measurable. Any questions for this example? Since it is uncountable, so it is hard to like write it very clearly about the coordinates and like some intervals.
I think intuitively you can try to understand it like because you try to take the limit, then you take the limit, this sequence of a limit is only countable, right? So there will be some index such that this index is not really described in this way. So that you
right.
find this kind of Jn.
Yes, right.
And beta. Mm-hmm.
Yes. Okay, let's go next. It's very time consuming for this one. Let's see one exercise.
By the way, where's Holly? Where's Holly? Holly seems well,
Holly is absent.
Yeah. Maybe we should wait her for like a minute.
Yeah. Yeah. You can see the Laura. You can see this question first, as I show here. I think it's very similar to what I've learned in the analysis course. So this question. Okay, why Holly is still not here? Maybe.
Yeah, we should continue.
Yeah, we should just continue. So, Dora, do you have any ideas?
I'm trying to, but I cannot think of anything quite useful for this example.
For the first one, do you have any ideas?
What is our topological notion for convergence?
Topological notions for convergence. You mean for the first one?
Yeah.
Yeah, maybe I will remind you of the definition of the convergence given here. So, like the very basic definition, I think in the previous subchapters is not very useful here. It says that if we have a like corresponding to each open neighborhood U of like some X, this X is the sequence convergent to, we can always find some Xn belongs to maybe some set such that every neighborhood U contains some Xn, or contains all of these Xn that n larger or equal to n. So in the real line, basically means suppose we have this 0 point, this origin, and suppose we have a sequence, this 1 over n. We conclude that this converges to 0. That's because for any open interval, like center containing this 0, it always contains some 1 over n in this sequence. For example, if we choose epsilon, if we choose epsilon here, we can choose n as 1 over epsilon. Right, so for any n larger or equal to this integer, 1 over n. I will try that. Yeah. So this sequence converges to 0. So for this question, we can use a similar method here. So suppose we have a since f is defined as R to R, so we can use the similar method here, right? To show that fn x minus fx less than epsilon. And the formal definition may be dfn x fx is less than epsilon for any epsilon larger or equal to 0. Oh, okay, so I will. I think we will run out of the time, so maybe I will just introduce how to show this. Yeah, this is all done myself, so maybe some errors here. Yeah, once you find some like flaws, you can just tell me, and I will revise it. So, if by the definition of the the uniform, just the convergence. So we want to find some integer n such that for any n larger or equal to this integer, the metric between fnx and fx is less than epsilon for any given epsilon. So in the real life, the metric can be defined as like this distance between these two, right? And fx is the zero function. So we just need to show this. And from the figure given in the 21.1, we find that the value of this fx is always larger than 0. And from this equation, we can also see this. It is a square times a positive number and plus 1, and it's of course larger than 0. So we just write this way. And we just need to show that for each x, this inequality always holds. So the main task here is to find a proper n for any given x. So since we are given x here, it is for each x belongs to the real line. So maybe suppose the given x is x0. So we have this given x here. And for any given epsilon, we can find an integer n such that when n larger or equal to this integer, this inequality always hold, right? So how to find this n? We can just use some like transformations of this whole, how to say, fraction. So this one is of course less than this, right? Since the denominator is smaller, so the fraction is larger. And we can use some algebraic transformations, and we get that. I'll check my notes. It's right, and use the similar technique, we can cancel this one. This is also larger than the fraction before, right? Because n is larger or equal to 1. So for this one, also for this one, since n is larger or equal to 1, right? So n cube is larger than this one, right? So we can make it smaller here, and the whole fraction become larger. So finally we get 1 over n squared times x0 squared minus 2x less than epsilon. So for any given epsilon, we can choose this n. Where n is the smallest integer that larger than this, bigger than this term. So for any given epsilon, we can always find this integer, right? And x. So that means f(n)x converges to x for each x belongs to R. Any questions so far? Okay, for the next part, if no, but for each x belongs to R, f(n)x converges to x, fx, right? But fn does not converge uniformly to f. So that's because the definition of uniform convergence, see that the delta epsilon condition holds for all x, all n, and x in the given condition, right? So that's the difference. And that means the converse of these theorems does not hold. Right. So how to show this one? Similar before, we want to find an integer n such that when n larger or equal to this bigger than n, this term is less than epsilon, right? But x is random here, and we need to choose an n. So x is unknown, but n. So we can suppose that we have an n such that this condition holds. So that means n is settled here, right? And then we finally find that we cannot actually find this n. So let's do it here. Okay, let me rephrase what I said. I think it's not very clear. So how to prove that it does not converge uniformly to F? So how to prove it converges uniformly? Basically, we need to find an integer n such that when n larger or equal to this n, this term is always less than epsilon, right? And this is for all x. So if we can conclude that for any integer n, there exists some x such that fn x can always larger than given epsilon. That means this inequality does not hold for all x. So fn does not converge uniformly to f. Is that more clear now? Okay, so the main task here is to find for any given n. So n is given. We want to find some x such that this term is larger than epsilon. So this is the function given here. I just plug in, and how to find the required x? We need some operations. So basically, we need to like know the range of x through this part, right? So that means we suppose this equals to m, and we want to find that n cube m plus 1, this one larger than epsilon. So use some transformation, we finally get that. So that means for this x, where x like it is in the any neighborhood of this given n, 1 over n, which is less than this value. For this x, this inequality is larger than epsilon. So that means for this x, the less than epsilon inequality does not hold. So we cannot find such n that this inequality holds for all x. That means it does not converge uniformly. Is that clear? I think it's more analysis. Okay, if no more questions, we'll just end it here. Yeah.
Thank you, Zikang.
Okay, thank you, Dora, for listening. So next time is Friday, right?
Yeah.
Okay, so see you next time. Yeah.
See you.
Okay, see you on Friday. Bye.
See you, Professor. Thank you.
Bye-bye. Thank you all.